Welcome to qnawire.
Alright guys, we're doing problem 82 of chapter 8 in Chemistry Essential Science. So ionic compound CaO crystallizes with the same structure as sodium chloride. In this structure, how many O2 are in contact with Ca2 plus? So look at figure 8.4. You can see that you have a cubic structure of alternating O2 minus and Ca2 plus. You can basically, if you were to go to the center of that, you can basically see four interactions that are in a plane, and then one up and one below. It's basically an octahedral structure. So, so there would be six oxygen O2 ions interacting with each Ca2 plus. So they want to know, would energy be consumed or released if a crystal of CaO was converted to a collection of widely separated CaO ion pairs? Energy be consumed, because in order for you to convert a crystal structure of calcium oxide to ion pairs, you have to break several of those specific actions. You have to break those favorable actions that would form a octahedral crystal structure, and you would have to break those in order to separate your calcium and your oxygen into specific ion pairs. So that's going to be energetically unfavorable because you're breaking bonds. So from the given ionic radii I calculate the potential energy of a single Ca ion pair that is touching the magnitude of the electronic charge given on the inside back of the cover. So we're going to use E is equal to K Q1 Q2 U over R. And K is going to be our electrostatic constant. Hence our Coulomb constant. And so E is equal to 8.99 times 10 to the 9th. Calcium and oxygen are using a negative charge, are each having their own charge. So we can write this as 1 point have a 2 plus 2 charge. So our elementary charge is 1.6 times 10 to the negative 9th. So we can write that as 2 times 10 to the negative 19th times negative 3.2 times 10 to the negative 19th. And our ionic radius and our R is going to be the sum of our calcium is going to be the sum of our calcium and our oxygen. .14 plus 1.26, and these are in angstroms, so we're going to convert them to meters. That means E is going to be equal to 8.99 times 10 to the 9th times 3.2 times 10 to the negative 19, okay, 0.14 plus 1.26 times 10 to the negative 10th. So this is going to be 3.84 times 10 to the negative 18 in joules. So to calculate the energy of a mole of such pairs, so we're going to have to multiply this by Avogadro's number, joules, with 6.02 times 10 to the 23rd moles. Third is equal to 2.3 times 10 to the 6 joules per mole. What factor do you think counts for? So how does this compare to the lattice energy of as this compared to the how does this compare to the lattice energy of calcium oxide? Oh, by the way, I forgot to put the minus sign here. Minus. So if we compare this to the, let's just put this as minus 2300 kilojoules per mole. Let's compare this to the lattice energy for calcium oxide, which is going to be minus 34.14 kilojoules per mole. And you can see that the lattice energy for calcium is significantly more negative, or rather significantly more negative than what we've calculated here. So it's a more favorable interaction. So they want to know what factor do you think counts for most of the discrepancy between the energies of part D? Do you think the bonding in CaO is more covalent than ionic? I would doubt it, because calcium is very metallic and oxygen is very non-metallic. Or the electrostatic interactions of crystallizes are more complex than a single ion pair. That is correct, because in a crystal lattice, you don't just have one single ion pair, you have multiple ion pairs that are interacting in a three-dimensional shape. It's not the same as a linear pair. So you are going to have more favorable interactions in your crystal lattice structure than you will have, than you're going to have in your single ion pair.